In this lecture, we'll discuss the partial autocorrelation function. If you recall from our previous discussion of the identification procedure, we will first look at if the data should be transformed, if there are any trends we need to take care of, and if periodicities that we need to model, and then we'll come to the model selection. This is the part that we're going to discuss today. So we are interested in how should I select appropriate models for the data I have observed. As you already know, you can look at the autocorrelation function to see that this will turn to 0 if it seems suitable to model it using an MA process. We need something similar to determine whether something is suitable to model as an AR process. So as you know, the autocorrelation function will turn to 0 as soon as I've hit past model order Q for an MA process. Can we do something similar for an AR process? The answer is yes, and this is the partial autocorrelation function. You compute it by computing the A coefficients of different orders and looking at the last coefficients in your model. Expressed simply, that means that if, say, for instance, I have an AR2, like this, that means that I should expect my A2 coefficient to be statistically significant. But if I were to estimate an A3 coefficient, that's not going to be there. So when you form the Pacf, you are estimating AR models of different orders and looking at the last coefficients. Basically, this means that I will begin by saying, well, what is it an AR1 model when I'll estimate the A1 coefficient? That is, of course, going to be something that's different from 0. Then I will say, oh, is it an AR2 process? And I'll estimate the A2 coefficient, and that's also going to be different from 0. Then I'll say, oh, no, it's an AR3 process, and let me estimate the A3 coefficient. But now, since there is no A3 coefficient, because this was actually an AR2 process, this should then, in theory, turn to 0. And this is actually all there is to the Pacf. For some reason, the notation in literature is that you use the negative A coefficients here, so express them called theta K1. That is the same thing as saying that I'm estimating the negative A1 coefficients of a model of order 1. And then I move up to saying that let me estimate the kth coefficients of an A process of order K, like this. So I form the Pacf in this way. The important part is, however, that the Pacf will then be non-zero if I'm lower order than P, whereas they will turn into 0 as soon as I pass model order P. Asymptotically, I can see that the Pacf will have a mean of 0 and that they will have a variance of 1 over n, that they are also going to be asymptotically normal distributed, just as the ACF coefficients are. That means that I can find a 95% confidence interval just as before, which is plus minus 2 over square root of n, just as for the ACF coefficients. This leads me to the following scheme. If my ACF has the behavior of being a damped exponential or ringing behavior, then an AR model is suitable. Then I should expect the Pacf to turn to 0 as soon as I pass order P. Similarly, if my model is more appropriately modeled as an MA process, then I expect the ACF to turn to 0 as soon as I pass model order Q, whereas I expect my Pacf to be having the ringing, damped exponential behavior. These two are, of course, mirrors of each other. For an ARMA process, both the ACF and the Pacf will have a ringing exponentially decaying behavior that will start at lag P minus Q. In general, it's quite difficult to see this P minus Q and use that to determine the model orders for these polynomials, but you can see that both the ACF and Pacf are ringing, and that would be a good indication that it should be modeled as an ARMA model. There's also something called the IACF that I will talk about in the book briefly, but this is normally not working very well, so we will ignore that. Here's an example when I can see the ringing behavior in the ACF, whereas I can see that the Pacfs turn to 0 as soon as I pass model order 2. So therefore this would be an AR2, would be a reasonable model here. So that means not that it is an AR2, but it means that the model is reasonable to use. Notice that there are no AR or MA processes or ARMA processes out there generating realizations for you. It is nature you are observing. There are measurements of some form or another, and you're asking yourself whether an AR model would be suitable to describe what you're seeing, or an ARMA model is more suitable. So you are not looking for some truth in the sense that it really was an AR2. You are looking for what is a suitable model for the data you have observed. Here's another example. This is an MA3. I can see that by the ACF having coefficients 3 being significant, and then the fourth coefficient going to 0, and I can see that I have something that has a sort of ringing behavior in the Pacf. Notice here, though, that I should be able to say that, well, this might instead be an AR4 or 6. So should I here use an MA3 model, which was actually how the data was simulated, or should I here use an AR4 or maybe even AR6, which would be the better model? Again, it's not relevant how I actually did simulate the data here, because it's not the truth that is out there that you're looking for. You are asking yourself what is a suitable model. Here in this case, it was an MA3, but that doesn't mean that that might be the model that we want to use to describe it. In general, it is better to use AR models if you can get away with it. The reason for this is that it's easier to estimate the coefficients in the AR model, and they are also more reliable. reliable. Whereas it's difficult to estimate the coefficients in an MA polynomial, and they tend to be a less reliable model for that reason. So that means that even though this was actually an MA3 model that I used when I simulated the data, in this particular case, I would have started out and say, I will try an AR4 model first and see if it's good enough. And if it's not good enough, I will move over to an AR6. And if that is not good enough, then I will try an MA3 at the third stage first. Notice here, why do I start with an AR4 instead of an AR3? Notice that the coefficient here is quite small. Is it outside the confidence interval, or is it just slightly outside the confidence interval? Should I treat this as 1 over the 20, or should I say this is actually statistically significant? That is not easy to determine. The only way to determine that is to try the model and then to see what works and what doesn't work. And then remember our KISS rule, we'll try the simplest model first and see if we can get away with it. If we can get away with it, we're happy. A smaller model is always better. It's more robust. It's easier to estimate the coefficients, and it's going to be more reliable. But if it's not good enough for us, then we will extend it by adding parameters and then see if we can get away with that. And if not, then we'll try to change the model structure and say maybe it is an MA instead. In this particular case, since I have a 1, 2, not 3, and 4 being clearly statistically significant, I would have used my initial model like this. Notice that I did not take the A3 component in because it's clearly not statistically significant. So even though I will use an AR4 model here to describe it, I will assume that the third coefficient is going to be 0. For every additional parameter in your model, your estimation accuracy will be worse. That means that the fewer parameters I have in my model, the better quality I will get on those parameters that I estimate. I therefore do not wish to estimate the A3 coefficient here if I can avoid it, because that will make the other parameters estimates being of a higher quality. If I were to say that this was not a sufficiently good model, then of course I would need to add the 6th coefficient, but I will not add the 5th coefficient because that is clearly not significant either, right? Here's another model. Here if I look at the Pacf, you can see that it has a very clear ringing behavior. And if I look at the Pacf, I do have ringing behavior, but it then turns to 0. Maybe I should use a model AR7 here to describe this. Or should I use an ARMA? In this particular case, the data was indeed simulated as an ARMA for 3 process, meaning that P minus Q would be 1. So I should have this first component behaving differently, and then there would be a ringing behavior in this. That's not very easy to see, and I would actually have not used an ARMA model as my first model for this one. Rather, I would have used an AR with 1, 2, 3, 4, 5 coefficients, an AR7 with 5 coefficients. That is the model that I would have used initially to see if I can get away with it, even though the actually simulated data was an ARMA for 3 process. And again, it doesn't mean that that's the model I want to use when I describe what I'm seeing. You could not expect to know that something really is an ARMA or an AR process out there. You can only see data and you can decide on a model that seems suitable for the data you're observing. And in this case, I would have used an AR7 model with 5 coefficients and not the ARMA model, although that is actually in this case the correct. Here's another example. I can see a clear ringing behavior in the Pacf, and I can see that the Pacf goes to 0. So this one is easy to say that an AR4 model should be suitable. Here's another example. You can see that the Pacf is clearly ringing, suggesting that I should have an AR or an ARMA structure to this model. And if I look at the Pacf, I can see that I have 3 non-zero coefficients in the Pacf, suggesting that I should use an AR3 model here. In fact, this is an ARMA 2-1 model when I simulated it. Again, showing you that I simulate something using an ARMA model doesn't mean that it's necessarily the model I choose when I look at it. Again, I do not have realizations of processes. I have data that I'm trying to find models for. And in this case, an AR3 model seems to be the suitable one. Finally, let's look at the sunspots. These are the sunspots that Schuster was studying, and if you look at the Pacf for these, you can see that I have a very strong and clear ringing behavior, suggesting that an AR part should be useful for my model structure. If you look at the Pacf, you can see that I have 2 statistically significant components in my AR, so an AR2 seems to be a suitable model, and this is in fact a model that is quite commonly used to describe sunspots.